to start recording. But today we're basically going to look at a lot of examples of solving these polynomial equations. But the first thing you always want to do is for every single problem, like if you're asked to solve or factor a polynomial equation, you always want to look for a GCF. If you can pull out a GCF, it's usually going to turn your problem into something easier to work with. Like for example, if you have a power of 3 and you can pull out an x, well, now you've got a quadratic instead of a cubic function, which we have a lot more tools to deal with quadratic. So you always want to look for a GCF because it can turn a problem that might take a few minutes to solve into a problem that will take less than a minute to solve. So it's always worth the time to kind of think about if you have a GCF. After you pull out your GCF, if it's possible, if you have a binomial left over, you want to ask yourself, well, is it a difference of squares? Because if it's a difference of squares, then you can just simplify it. If it's a binomial that you can solve, just solve your binomial to get the answers from that. Like set that binomial equal to 0 and solve it. Like for example, if you just had x minus 2 after you solved, well, I mean, you could easily solve that your 0 would be at 2. A new thing we're going to look at today, we'll see if we get to these or not, is if it's a sum or a difference of cubes. We're going to have like formulas to kind of deal with those, and we can see those can be kind of a pain to deal with, but we'll see if when we get to those later today, or we might not get to those till next week, or depending with the midterms and stuff. If you have a trinomial left over, well, see if you can factor it. You might have to use grouping, or you might have to use like quadratic formula or completing the square. But always like with the trinomial, see if you can factor it first, because usually that's a lot faster than say quadratic formula or something like that. So we're just going to look at a lot of problems. We're going to see, like I said, most of these problems are kind of designed to work out nicely today, but keep in mind, like we will learn a method later in this chapter that will work for problems like if you can't pull out a GCF or you can't turn it into something you can deal with. There's going to be like a backup method later on in this chapter. So I'm going to do like an example, or like some of these are all different. I'm going to have you guys try some of these, see if you can do it. But like I said, for example, 1, I mean, the first thing you would do is check, is there a GCF? Well, first off, in terms of like the coefficients, I can pull out a 2. Oops. And they both have an x in them, so I could also pull out a single x. So when you pull out a GCF, remember, you're really dividing each piece by that. So I would have just x squared, and then I would have minus 9. And then we're going to just basically see, can we solve each one of these pieces? I mean, for this, I would just set 2x equal to 0. So I would just get x equals 0. For this, if you recognize, this is a difference of squares. So remember, x squared minus 9, you could rewrite that as x plus 3, x minus 3. Or like another way you could think of it, if you didn't recognize like that shortcut, remember what multiplies to -9 and would add up to 0, really, because you have a 0x there, even though we don't write it. So that would be +3 and -3. But then you would get your other solutions are at -3 and +3 if you solved like each one of these binomials. So as you can see, like we don't have a method really to solve this x cubed, but once we factor that out, it turned it into a quadratic and then a linear part that we could solve each one of these pieces. So that's why you always want to look for a GCF, because it's going to make your life, or it's going to turn it into a problem that you have the skills to do. Problem 2, I want to do this one quick. Honestly, this is something I haven't done a lot, but if you ever see you have a 4-term piece, you want to see if you can do that grouping process. Like basically, you're going to look at your first 2 terms and your last 2 terms, and you want to see if you can plot a GCF from each one of these groups so you get the same thing inside your binomials. So like from that first set, I could pull out an x squared. So I would just have an x minus 5. And we want to see, is there anything I could pull out of this group that would give me x minus 5 on the inside? Well, if you notice, it's the same thing, just your signs. You could pull out a -1, and that would turn it into the same thing. So you can do this grouping process. It won't always work, but if you can get these to be the same, then you've got your answer. So we would have x squared minus 1, and we would just have an x minus 5. So I mean, the solution from this part would just be 5. This we would want to solve. I mean, really, you would set this equal to 0. You would add 1, and then you would square root both sides. So we would also have plus or minus 1. And I don't need to see your work for this. Like if you could solve x squared minus 1 equal to 0, like in your head, like especially when you do a lot more of these problems, like you're probably going to just see, oh, that would be plus or minus 1. Like I don't need to see that like worked out, if that makes sense. So how about you guys try number 3? I'm just gonna I'll give you a hint. It's going to be a difference of squares, but see if you can factor number 3, and then what would your solutions be? So give this one a try. I'll pause the recording with you one. So if you did your difference of squares, remember it's like what would give, like what times itself would give you 4x? Well, that would be 4x squared. Sorry, that would be 2x. And then 81, like that's a perfect square, that would be 9. So this would really be 2x plus 9, 2x minus 9 if you do a difference of, like if you use that difference of squares formula, because like this is really 2x squared minus 9 squared. So like a is 2x and b is 9. I don't know how we're all doing with difference of squares. Hopefully that's something we're doing all right with. You could also honestly factor this with the square root method. You could add the 81 over, divide by 4, and then square root. So this one you could actually solve in different methods as well. But if you solve this, like if you set 2x plus 9 equal to 0, you would subtract the 9 over, then divide by 2. So you would get positive 4. Well, this one would actually be negative. And then from this one, you would get positive 4.5. But just so we're clear, this is what I don't need to see your work because I'm assuming a lot of you guys can probably do this in your head. But like you would subtract the 9, then divide by 2, and you should see you get those answers. But when you're working these out, I really don't need to see your work because especially for a lot of these, I'm going to kind of assume you're getting to a point where you can kind of do it in your head. Someone asked if we should leave our answers as fractions or decimals. Personal preference. Doesn't matter to me. A lot of times I like decimals because especially if you were like graphing these zeros, it's easier to think about decimals versus fractions. But then again, fractions you don't have to round ever, so I don't care. But so, oops, some teachers might have more of a preference, but for me, I don't know. I usually like decimals myself, though. All right, so those are the first 3, and I really spaced these out, so sorry if you printed these out. We're going to see some of these get a little bit messier. But like I said, you always want to check for a GCF. So if you look at problem 4, I mean, like I said, a lot of these problems are working out nicely. Like we're going to see some problems where you can't pull out a GCF and you're like, well, what the hell do I do now? Well, we'll learn about those later. But these ones all kind of work with this method. So it's always worth checking if you can do it like we're doing these right now, even for later problems we see in this course, because you can save yourself a lot of time if it works in this way. But for this problem, you could pull out a 5x. So if you do so, you would have x squared plus 3x plus 2. And notice with all these equations, you want to make sure it's equal to 0 before you start doing this, because that when you solve, you want to have your equation equal to 0. So then you want to see, well, I mean, this 5x part, I mean, if you set 5x equal to 0, you're just going to get x equals 0. But then for this trinomial, you want to see, well, can you factor it normally? If so, awesome. Worst case, if it's not something you can factor, you're going to have to use like quadratic formula or group in or a different method. But this one factors nicely. Like it would just be x plus 2, x plus 1. So you would get 2 more zeros or 2 more solutions at x equals -2 and x equals -1. But But notice once you pulled out your GCF, well, now this is something we can deal with, versus like if we didn't pull this GCF, well, how the heck do we solve something with this x cubed? Well, I mean, there really isn't a method that you know of yet. So that's why you want to make sure you look for a GCF. If you can turn it into like a problem, like or a quadratic or something we've seen before, or you know how to solve. Number 5, same idea. You could pull out a 5. Unfortunately, you can't pull out like the whole coefficient, but that would turn it into this. So how about you guys take a second, see if you can finish problem 5. You could use grouping for this problem. You could use quadratic formula. You could probably do completing the square, but I honestly probably wouldn't recommend that for this problem since you're going to have like decimals and stuff. But if you really like completing the square, you could do it. But see if you can finish factoring out this number 5. Like I said, you could either do grouping, you could do quadratic formula. And honestly, in this chapter, I'm going to always leave that choice to you. I'm never going to like tell you how to solve something. So if you see a quadratic, you can basically choose any method you like. So if you like the grouping method, do that. If you like the quadratic method, do that. Keep in mind the grouping method might not always work. I mean, quadratic formula always works, completing the square always works, but if you try and do grouping or factoring, it won't work for every trinomial you see. So, but usually a lot of times those are quicker than quadratic formula necessarily. So, but see if you can finish up this question. And let me just see. One of your answers will be a decimal. You'll get one whole number and one fraction or decimal if that. And your work could look different than mine. So there's different methods. I'm going to do the grouping process. So remember that I would basically multiply my A times my C. What multiplies to -6 and adds up to -5? Well, that would be -6 and +1. So I would basically rewrite this. And then we want to do that grouping process, kind of like what we saw almost in, I believe, number 2. So if I do this, I mean, this 5 is just going to stay out here, but I could pull out a GCF. It would be 2x for this one. And then for this one, I mean, it's already, if you notice, it is basically x minus 3. So there's nothing really I can pull out of that second one. So you need to at least put a 1. How did I get -6? You remember if you have a coefficient in front of your x squared, you got to take that 2 times that -3. So if you have a value that's not 1, you got to take it like what it's going to multiply to your a times your c. But this would just be the same. So remember when you put this together, you put your GCFs in a group. So that would be the 2x plus 1, and you copy one of those x minus 3s down. But if you're not super comfortable with grouping, like I said, you could do quadratic formula for this problem. I mean, it really wouldn't be too much more work, if any. Sometimes I like quadratic formula because grouping, sometimes you have to think. And with quadratic formula, you really don't have to think too much. You're just kind of plugging it in. But if you solve these, if you solve this, you should get -1/2 or -0.5. And then if you solve this one, you should get +3. Because keep in mind, I didn't write this should still be equal to 0. I didn't write that part. So you would just have 2 solutions. And you're not going to get a solution from this part because there's no x. So the 5 really doesn't do anything in this problem. All right, I want to look at one more. This 6th one's a little bit messy. First thing we want to make sure is you want to get everything to the same side of your equation. When you're solving, you always want these to equal 0, unless you're doing like the square root method or something like that. But pretty much, if you're doing quadratic formula, if you're pretty much all of these problems, you pretty much usually want, unless you're doing something specific. But and one thing is when you move it over, you want to put this in standard form. Like you want to have the highest power, then the next highest power, then the next highest power. So I'm going to kind of like rearrange this. So I'm going to put that minus 6x cubed in the middle, because like I said, I want it, if possible, it's nice if you can get it in standard form. So then we want to pull out a GCF. Well, I can pull out a 3 and I could pull out an x squared. So that would be just x squared minus 2x plus 4. Right? Just double check myself. But yes, okay. So I'll make sure I don't make a silly mistake. So then, I mean, this you're just going to get x equals 0. Technically, since it's an x squared, if we were graphing this, it would have a multiplicity of 2. So it would actually, if you remember, like in our graph, it would bounce at that location. But we're not graphing or sketching these, so you don't have to put that. But technically, this one would have a multiplicity of 2. And then we want to factor this. The problem with this one is you can't factor this nicely. Like there's nothing that multiplies the 4 and adds up to -2. So this situation, we're probably going to get imaginary solutions if you see something like that. So we got to do quadratic formula really quick, which kind of sucks, but we're going to see in a lot of these problems, you got to do quadratic formula. So hopefully we're pretty competent with that. Like it can be a pain, but hopefully it's not something we struggle with. Don't get me wrong. Like no one's ever excited like, oh boy, I get to do quadratic formula to solve this. No one's ever like that, but it shouldn't be something like that you're dreading. It's more of a pain to do that. So if we do quadratic formula, yeah, what's going on, Aaliyah?
I said I am. That's my favorite one.
You like quadratic? Okay, good. I mean, because it shouldn't be like a thing you hate, at least. I mean, other than sometimes it's annoying to do. Don't get me wrong. If I could, I would rather do like a factor tree, but you can't do it for this problem. So if we plug it in really quick, we would have, remember the formula is negative b. So it would really be positive 2 in front because -2 plus or minus b squared. So -2 squared minus 4 times our a times our c all over 2 times a. I'm just going to start cleaning this up here. So we're going to have 2 plus or minus over 2. If you work this out, like if you put this in your calculator, you're actually going to get an error, like a negative number or an error if you try to put the whole thing in. But that would really be 4 minus 16. So you're actually going to get the square root of -12. If you like work that out. Let me make sure I'm not mistaken. Is that what I? Oh, I actually saw, you could actually have done this problem with completing the square. Actually, you'll see if you look at my key, I did this by completing the square, not quadratic formula. But so if you want to clean this up, I mean, it depends really like what your teacher really cares about, but the square root of 12, I don't know what that is in decimal form. What would that be? I think it's 1. Is it 1 point? That's not right. Let me just put that in my calculator really quick. Sorry, guys. I mean, you could, well, I guess you could keep it in radical form too, I guess. It kind of depends. But the square root of 2, I usually like to sometimes get a decimal. It's roughly 3.46. And then if you want, you could divide both parts of these by 1. You could also write it like this, 1 plus or minus. And then half of 3.46 is roughly 1.73. So you could also write it like this if you'd like. Especially when you get imaginary solutions, I'm usually not too picky how you write it. But how I wrote it here is probably how a lot of teachers would like to see it maybe in the future. But especially when it's imaginary, usually you're not doing too much with it. So these first 6 questions, I mean, I know they're technically new because like we never looked at solving something with like an x to the 4th in it in chapter 4, obviously, when we were just looking at quadratics. But the key thing I want you to get out of here is if you can pull out a GCF, usually you can a lot of times you can turn these problems into things you can solve based on the skills you already have. This will not always work because, like I said, later in this chapter, we're going to look at problems like maybe you can't pull out a GCF. Well, what do you do then? Well, we'll have to learn a different method. We'll have to learn a new kind of way to go about it. But anytime you can do this, it's definitely worth doing because you're going to see that new method we learn at the end of this chapter. It's not hard, hopefully, at least once we get it down, but it's kind of a pain. It's like a process. It can be kind of like a pain. Like it takes time. That's what I'll say. But if you can do this, this is definitely faster. So it's always worth to kind of look if you can pull out a GCF and do something like we are on these first 6. So we've got about 10 minutes. We're probably just going to get to look at these perfect cubes. I don't think we're going to have enough time for these last 2 examples if you have these notes, if you printed them out, or if you're looking at them in front of you. But I want to start looking at this sum of cubes and difference of cubes. And I'm going to be honest, these can be kind of a pain to solve. But once you get this down, they're all pretty much the same process. So one thing you're going to want to recognize are perfect cubes. I don't know if you know your perfect cubes, but like 1 to the 3rd power would just be 1. 2 to the 3rd power would be 8. 3 to the 3rd power would be 27. 4th to the 3rd power would be... Wait a minute, 4 times 4, 16 times 4 would be... I'm not going completely brain fart right all of a sudden. 16 times 4. Okay, that would be 64. Geez, I don't know why I had such a brain fart. 5 to the 3rd would be 125, so on and so on. But hopefully you're eventually going to want to recognize some of these perfect squares. Because if you have something that like an x cubed plus a constant that's cubed, you can use this formula, this sum of 2 cubes or difference of 2 cubes. One way to kind of remember these formulas is the acronym SOAP. It's the same, so if it's a plus, you have the same sign, the opposite sign, and then this last sign is always going to be positive. Same thing if it's a minus, you're going to have the same sign, the opposite sign, and then it's always positive for that final sign. So like if you kind of look like these formulas, it's basically this, you have an A and a B, either plus or minus, and then you have this A squared minus AB plus B squared. So the only difference between these are the signs, but if you kind of remember the SOAP acronym, it can kind of help you remember these formulas. Usually I make my students memorize these formulas, like you should know these, but realistically, I mean, you're going to be able to reference these formulas, so you don't have to memorize them, but it's something you might need to kind of memorize at least in a future class. So just kind of keep in mind. I don't know how much that's a big if, because I'll be honest with you, I don't know how much you'll do with difference or sum of cubes in your next class. You might not really touch them a lot, to be honest with you. But I still want to show you, just so if you do see them next year, you're definitely not completely caught off guard. All right, so basically with these problems, so like in this problem, like I have x to the cube, so my a is x, and then 64, that's a perfect cube. Like my b would be 4 in this formula. So this is a sum, so I'm going to be using this formula. So I would just have x plus 4, like the same sign, and then I'm going to have x squared, the opposite sign, a times b, that would be 4x, and then plus b squared, that would be 4 squared, or 16. And then we need to solve these. So I mean, this first part, it's going to be -4. For this second part, you're always going to get imaginary solutions. So you can either do complete in the square, or you can do quadratic formula. I usually just use quadratic formulas for these, but if you like complete in the square, that would also be a valid method. All of these problems, you're basically going to have to complete this, or use, I usually use quadratic formula, like I said. So it's -b, so that would be +4 plus or minus, and I should have given myself more space. I don't know why I didn't space this one out more, but we'll see if we can squeeze it in. So then it would be b squared minus minus 4 times a, which would be 1 times our c, all over 2 times a. Gosh, I did not give myself enough room. If we start cleaning this up, though, we're going to get 4 plus or minus, and the bottom, it's going to be 2. If you work this out or put this, like what's underneath in your calculator, you're going to get 16 minus, that would be 4 times 16 is 64. Really, like this, if you kind of simplify this out, that's really 16 minus 64. So 16 minus 64, let me just make sure I don't do any embarrassing Mathematical error, 16 minus 60. Yeah, 16 minus 64 is negative 48. So we really have the square, oops, not the highlighter. So in the square root of 48 is roughly 6.9. I'm just going to cross this problem out because I'm using way too much space. But basically we would have x equals negative 4. And then from this, if you want to, like, I would just leave my answer like this. You're going to have plus or minus 6.9i over 2. If you want to divide both of those parts by 2, you can. Someone asked if I can show completing the square. I'll do the next problem. I'll do it by completing the square, just to kind of show you a different method. But quadratic formula is usually my go-to for these, to be honest. But it's really up to you. Completing the square would totally work with most of these, and it shouldn't be too bad, because you're always going to just have an x squared, so you're not going to have a coefficient. So okay, I'm going to cross out number 4 as well. I'll do one of those below. How are we doing on time? This might be the last one I get through. I forgot the negative 4 in front. That should be a positive 4 because it was negative 4, if I'm understanding right. Yeah, because that yeah, I just added it like technically it was negative 4, so I just put a positive 4 there. All right, let's look at one more, a difference of cubes. We'll definitely look at this some more either tomorrow, or like I said, we might kind of have a break with our midterm, but this is definitely something we'll spend more time with, because I don't expect you just to like, oh, I completely understand it after seeing one problem of these. These are a little bit strange. I get it, but your A in this one would just be x. Your B, what's 27? Like, what's the perfect cube? Well, 3 to the third power is 27, so that would be 3. And since it's a difference of cubes, I mean, we're using this formula. I mean, it's the same formula, just your signs are different, but it's your A minus it's your same sign. So it would be A minus B. So x minus 3, and then it's x squared. And then it's the opposite sign. So plus A times B in this problem would just be 3x, and then always positive. So plus B squared would be 9. So, I mean, from this part, you're always going to get one real solution, and then you're going to get 2 imaginary solutions. So all of these are going to work. Oh, gosh. I'll do completing the square for this one, but it's an odd number here, which is unfortunate. Usually when you do completing the square, it's always nice if you have an even number there. Here, I'm going to do quadratic formula for this one. I'm going to wait till I get a better one to complete the square, or I'll just do a separate problem. But I don't want to deal with the decimals. So I'm sorry, you can yell at me if I know I'm not listening to you, but this would be -3 plus or minus 3 squared minus 4 times our A is 1, our C is 9, all over 2 times our A, which is 1. So if we clean this up, this would be -3, this would be 2 plus or minus. This would really be 9 minus 36. Like I said, when you're doing these difference of cubes or sum of squares or sum of 2 cubes, geez, if I can speak properly, you're always going to get imaginary solutions with this second trinomial. Like, you're never going to get nice answers. So you're pretty much always going to get I's with this second part. So that would just be 9 minus 36. So that's -27. Oops, not the highlighter. So if you want to just clean this up a little bit, this would be -3 over 2 plus or minus. The square root of 27 is approximately 5.2. So this would be 5.2i. And you could leave your answer like this, or like I said, you could divide both parts by 2. But I would definitely just keep it as whatever plus or minus whatever. Like so for example, if you wanted to, you could write this as -1.5 or -3/2 plus or minus half of 5.2 would be 2.6. Right? Yeah, 2.6. So you could also write it like that. Some teachers might prefer it like this, but honestly, we're not really doing anything with it, so I don't care if you leave it as a fraction. Um, I might give you something in Delta Math. If it's in Delta Math, you're probably gonna have to write it like this, though, to be honest with you. I don't know if they would take the fraction or not. So we are all out of time. Like